All right. Hello, everyone. Welcome to the 20th online Spintronics seminar. Thank you for joining us. This is Xin Fan from University of Denver. It's my great pleasure to introduce our speaker today. Professor Tim Mewes is the IEEE Distinguished Lecturer for year 2020. He received his BS and PhD in physics from the University of Kaiserslautern in Germany. He subsequently was a postdoc researcher at Ohio State University before joining the University of Alabama in 2005, where he now works as a professor in the Department of Physics and Astronomy. His research interests include magnetization, relaxation, mechanisms, micromagnetics, dynamics of magnetic nanoparticles in solution, spin transfer torque, magnetic random access memory, spin logic, magnetic resonance force microscopy, and materials for microwave device applications. Professor Mewes received many prestigious awards, including the NSF Career Award and the IBM Faculty Award. He currently chairs the Alabama chapter of the IEEE Magnetic Society. So without further ado, please.
Thank you, Xin. Really appreciate you giving me the opportunity to talk during your seminar here. Xin mentioned it, so I'm giving a lecture as the distinguished lecturer of the IEEE Magnetic Society. For that reason, I wanted to bring to your attention, if you're not a member yet of the IEEE Magnetic Society, what this society does. There are quite a few things that the Magnetic Society does. So you've got local chapters, and I know that the chapter in Colorado is a very active one. So if you're listening in from there, you're probably aware of all the activities. However, if you're in a different area, you might want to check out your local chapter and see what kind of activities, lectures are going on there. There's also there's a free summer school for graduate students, which was something I think a lot of students were looking forward to. Unfortunately, this will not happen this year, but there are plans going forward in the future. The Magnetic Society is also heavily involved in conference organizations. And again, we're struggling with COVID here, but rest assured that a lot of people are working behind the scenes to try and make the best of the current situation and trying to put together a virtual MMM conference. The other thing, the Distinguished Lecturer Program is something I enjoyed as a student. I still remember many years back when Tom Silver came to Kaiserslautern to give his presentation. And so this is something that normally I would be traveling around the world to give this talk. Unfortunately, I currently can't do that. But I hope that with this seminar, at least I can make up for some of the lost opportunities. So if you're not a member yet of the IEEE Magnetic Societies, I would really encourage you to check out the website and join if you are not a member yet. With that, I want to get to the actual content of my talk. So I'm working in a lot in magnetization dynamics, and the talk that I'm gonna give today is in particularly aimed at students that may not necessarily be that familiar with that topic. So I'll go into a little more detail about the basics and introductory topics, but eventually I'll get to some of the interesting research that we've been involved lately, including the intrinsic damping in iron and anisotropic damping, and we'll see how that goes.
Hi, Tim. Sorry to interrupt. Your audio has a little bit of noise. Is it because the microphone is scratching your clothes?
Could be. Can you hear me now? Better?
Yes.
Is that better?
Sounds better.
Okay.
Yeah. Okay. Great.
All right. So the magnetization dynamics, when we talk about magnetization dynamics, we can describe that with the so-called Landau-Lifshitz-Gilbert equation of motion, which is written down here, and you can kind of see the motion in that animation here. And this motion of the magnetization consists of essentially two terms. There's a precessional term, which is the first term here in this equation, and there is a damping term that leads the magnetization to actually align with the effective field. The effective field contains both the external field and internal fields like the exchange field, dipolar field, and anisotropy fields. And if you look at this equation, that actually might look familiar. And normally, when I give this talk in person, I would actually give a short demonstration. Unfortunately, I can't do that, so I have a little video clip here of the gyroscope, which is essentially the same motion. Part of this equation here is really just conservation of angular momentum. So you have the rate of change of the angular momentum equals the torque on the right-hand side. So that's the precessional term. And it's kind of, if you haven't held a gyroscope in your hand, it's actually kind of interesting to do that, where you really can feel the precessional term here. The damping term then ensures that eventually the precession will die out and the magnetization will align itself with the effective field. But there's one important difference in terms of the gyroscopic motion that you see down here. If you look at the precession frequency of that gyroscope, it may be of the order of a second or so. That is very different in magnetization dynamics. The dynamics is much, much faster for the magnetization, which brings me to the characteristic timescales in magnetization dynamics. And that's the numbers here are just kind of typical values. There's obviously a lot of parameters that you can play with to kind of change that, but the precessional dynamics, so a full precession happens in a fraction of a nanosecond, whereas the damping typically happens on the time scale of nanoseconds. When you then look at more complex dynamics like vortex and domain wall motions, those all typically happen at much longer time scales, which is kind of shown here schematically for a couple of examples. You also have spin waves that cover a similar time scale. However, there are faster processes. There's the exchange interaction, which is extremely fast. There's the spin transfer torque and spin orbit coupling. And so that kind of sets the time scale. So compared to the second time scale of the mechanical precession that you would see in a gyroscope, things happen a whole lot faster. Which kind of brings me then.
Tim, sorry to interrupt you again. Your voice, every once in a while, seems to be this noise coming out. How about let's try just directly use the audio input from your laptop? If you just unplug
Okay.
Yeah, thank you.
Try that. Can you hear me now?
Yes.
All right, good. Let's try that then. All right, so the which brings me to the actual time scales of these of this kind of dynamics. And so here's an example that shows the average magnetization of a thin disk as a function of time, and this is actually a simulation of that disk, where the disk is where the magnetization essentially realigns itself with an external field of 1.2 Tesla along the film normal. And so if you look at this information on the in the time domain, it's kind of difficult to figure out what's going on here. So why do we see these different oscillations? You might have some ideas, but typically what we do then in physics, we actually take the Fourier transform of the data, and things get a whole lot clearer once you do that. What you see is you see these pronounced peak in the Fourier spectrum. And so now you can actually start identifying those peaks. And what you see here is, for example, this first peak here in the power spectral density is just the fundamental mode of your disk. And you can show this as a color-coded map, or you can show it in 3D like this. And then you can go through the different mode profiles here that you see. And essentially what this tells you is that in this time domain signal, what you had is contributions from all these different modes that exist in this disk. And that led to this fairly complicated time evolution of the magnetization as it relaxes back to its minimum. So then what we can do now is we can, instead of looking at things in the time domain, we can simply look at things in the frequency domain. Obviously, nothing really changes. We're just changing the axis here. So we're looking at things now in the frequency domain, which brings me to the technique that you can then use to characterize these systems, which is ferromagnetic resonance. And so in ferromagnetic resonance, we probe the magnetization dynamics directly in the frequency domain. And the way this works is you apply an external, static external magnetic field, which then the magnetization will minimize the free energy of the system. And on top of the static field, you also apply a microwave field that is typically applied perpendicular to the static field. And then when you observe maximum precession, you observe maximum precession when the resonance condition is met. That is, when the driving frequency equals the precession frequency. And I always compare that with a kid on a swing that somebody like tries to push. You're going to have a hard time pushing that kid if you don't hit the right frequency, the fundamental frequency of that pendulum. And this is the same here. So you really will only observe large-scale precession if you drive the system at the right frequency. So we need to look into what the resonance condition is. And one way to write this down is the so-called Schmidt-Belyas relation. Don't want to go into all the details, but what you see is that the resonance frequency here is related to the second derivatives of the free energy of the system. And again, the free energy of the system will then contain the Zeeman energy, shape anisotropy, magnetocrystalline anisotropy, and so forth. And so by solving this equation, you can then determine what the resonance frequency of that system is under the given conditions. Obviously, in this form, it's not very instructive. So let's look at a simple case where we have a thin film. And in a thin film, things simplify quite significantly. And you end up with what is known, and it's been known for a long time, as the Kittel equation, which essentially gives you an analytic relationship between the driving frequency of your microwave field and the magnetic field at which the resonance then occurs. So the way to look at this is, if you drive the system at a given frequency, you can now tune the field to meet that resonance condition. There are a couple of things in ferromagnetic resonance. We cannot distinguish between the shape anisotropy and a perpendicular anisotropy, Ku here. So that's why we typically introduce what's called the effective magnetization, which includes both contributions. So you cannot separate those with a single FMR measurement. So over the years, ferromagnetic resonance has been used for quite a long time to precisely determine anisotropies. Question then is, so how do you actually measure that? Well, at resonance, when you drive the system at resonance, the system will absorb some of the microwave power that you supply. The power absorbed, the average power absorbed by the sample is proportional to the imaginary part of the susceptibility of the sample. And so you can now essentially take advantage of that. All you have to do is you have to measure the average absorbed power that is absorbed by the sample. And over the years, people have done that in slightly different ways. So initially, most of the work was done with resonant microwave cavities, which work at a single frequency. There was a period of time where people used shorted waveguide, which covers the frequency band of the waveguide. More recently, vector network analyzer, FMR, is quite common. The difficulty there is that VNAs are fairly expensive, so you're typically limited in your maximum frequency that you can cover by the budget that you have available. Another method that we also use in my lab is coplanar waveguide FMR, where essentially your maximum frequency is limited by the microwave bit design. And so here's an example of how that may look like. So again, you have the static external magnetic field, and perpendicular to that, you apply this driving microwave field. And so by combining different of these methods, we are actually able to cover a very wide frequency range, all the way up to 115 gigahertz. So really in the interesting part of the dynamics that we want to investigate. Here's another quick animation of how this works. So that's an actual setup. And so if you drive the system at a given microwave frequency here, in this particular case, that's at 20 gigahertz, and you drive the system, but apply a field that's below the resonance frequency, your precession cone will be very small. But as you increase the field and now hit the resonance condition, you get a large precession cone here of your magnetization. Consequently, the system will absorb quite a bit of the microwave power that you supply. And this is actually the resonance of your sample then. Obviously, as you increase then the field again, you will detune from the resonance condition. And again, the precession cone becomes very small. So what you get from a measurement like this is you can determine then from this line shape, you can determine the resonance field itself and the peak-to-peak line widths. And I kind of mentioned that earlier, the resonance field allows you already to very precisely determine anisotropy. You can also determine the gyromagnetic ratio, in some cases the exchange stiffness, and a couple of other things if you try hard. The line widths, and this will be the focus of the remainder of the talk, allows you then to learn something about the dissipation in the system. And it also gives you some information about inhomogeneities in your sample, like here, the inhomogeneous broadening, delta H naught. And what most people are most interested in is this Gilbert damping parameter that enters the Landau-Lifshitz-Gilbert equation. So now the equation here that links the peak-to-peak line widths with these interesting parameters is given here, and it's a simple linear relationship. So what that tells you is, well, the gyromagnetic ratio you can determine from the resonance position. So the only free parameter here is your damping parameter alpha. So if you're able to measure the line widths over a broad frequency range, you should be able to very precisely determine the damping parameter of your sample. So that's kind of as a little background. And obviously this damping parameter is immensely important for a number of things. It first of all determines how fast the magnetization relaxes towards the effective field, but it also determines the threshold current and spin transfer torque, MRAM, or in spin torque oscillators. It also determines the mobility of magnetic domain walls. And so, which leads us to the question, so what are the physical mechanisms that are responsible for the damping? And to kind of illustrate that a little bit, I want to give you a quick overview of what the mechanisms are that can contribute to the damping in different films. And I'll start off with extrinsic damping mechanisms, which are mechanisms that are caused either by inhomogeneities or other geometrical peculiarities of your sample. And the first one to mention there is called two-magnon scattering, which is caused by inhomogeneities, typically at interfaces. And if it's interfacial in origin, it scales like 1 over the thickness of your film squared. And that's a good handle that you have to try and determine whether two-magnon scattering contributes significantly to your line widths by just varying the thickness. And so how does it work? Well, you have this ferromagnetic resonance, or K = 0 magnon, which then scatters into a propagating magnon. And then eventually this will dissipate to the lattice. And this is to kind of understand how this works is what is shown here is the dispersion relation of the magnons for an in-plane configuration where the external field is applied in the plane of the film. And what you have here is at K = 0, that's the ferromagnetic resonance, and there are a whole bunch of propagating spin waves that are degenerate with the ferromagnetic resonance. So the K = 0 magnon can scatter into all these different magnons and thereby contribute to the damping. Another interesting part of two-magnon scattering is that it's absent in out-of-plane measurements simply because there are no degenerate states into which you can scatter. Which brings me to another damping mechanism, which is eddy current damping. So eddy current damping is just that. It's essentially the precessing magnetization causes eddy currents, which in turn then lead to dissipation. Again, the interesting part here for thin films, this would scale, or you expect this to scale like the film thickness squared. So you make your films thicker, you get more eddy current damping. And so that's a handle that you have experimentally to try and determine whether eddy current plays a role in your films. Then there's spin pumping into adjacent layers, which then act as a spin sink, which, because it's an interfacial effect, scales like the inverse film thickness. But I'm not going to talk about this because Satoru Imoro gave a talk about this topic earlier this week. So if you're interested in that, take a look at his talk. Which brings me then to the intrinsic damping mechanisms, which are probably the ones that we're more interested in from a physical point of view, because they are inherent to the material, they are unavoidable to some extent. And so the first one you might think of is the direct magnon-phonon coupling, which is expected to be small from theory. And I think over the years we've seen with the extremely low damping that we get in insulators, that this is indeed in typical transition metals, not the dominant limiting damping mechanism. Instead, in transition metals, spin-orbit coupling is actually the mechanism, the intrinsic damping mechanism that we need to consider. And so let me show that in a little bit more detail. So Kambersky, way back then, together with Brett Heinrich, they came up with this model. And essentially what this is the precession of the magnetization is able via spin-orbit torque to create electronic excitations, which then in turn via electron lattice scattering create phonons. And so that's your dissipation channel. You can obviously then describe that mathematically. I don't want to go into the details, but essentially you have this spin-orbit torque here, and you have the spectral overlap, which in turn then depends on the scattering rate which then itself depends typically on the temperature. And so let me give you a little bit more of an insight here. There are actually two main contributions that we consider when we talk about spin-orbit coupling. And they have to do with whether you scatter between bands, so where the band indices are different, so n is not equal m, so that's an interband contribution to the spin-orbit damping. And so the way this works here is as you lower the temperature here in this animation, you see that the overlap of these two bands at the Fermi energy actually diminishes. Therefore, what you expect for this contribution is that it decreases as you decrease the temperature. This is very different if you look at an intraband term where essentially you create electron-hole pairs in the same band. What happens here is as you lower the temperature, as you can see here, the density of states at the Fermi level for this particular band that we're looking at here increases, and therefore your damping parameter should increase as you decrease the temperature, and that will become important in just a little bit. So quite a while ago, together with Satoru Imori, we kind of noticed that there's actually something missing in the history, or in terms of our understanding, for a very simple ferromagnet, which is iron. So you would think iron is the prototypical metallic ferromagnet, so you would think everything is known about this. But if you look at the model that I just discussed before, there should be a term that scales like the conductivity. But all experiments up until that point did not really confirm the existence of this kind of a contribution. So what we did then in collaboration with Satoru Imori, we kind of tried to see whether we can actually find out what's going on in iron, whereas for nickel and cobalt, this kind of contribution had been confirmed a long time ago. So let's take a look at the system that we investigated here. These were epitaxial iron films that were grown on both MgO, that has a lattice mismatch of about 4%, and magnesium aluminum oxide, which has a much lower lattice mismatch of about 0.4%. And the X-ray diffraction kind of confirmed what we were hoping for. So the crystal quality, here's a rocking curve. Both films actually grow single phase and epitaxially on both substrates. However, the iron on magnesium aluminum oxide has a much smoother interface and a higher crystalline quality than on MgO. So that's something to keep in mind as we move forward. So one thing this leads to is if you just look at the conductivity of these films, is the better structural quality of the films grown on magnesium aluminum oxide means you have a lower scattering defect density, so therefore you get a higher conductivity at low temperatures, which you can see here as a green curve in this graph. And so this gives us now a model system to investigate the influence of structural disorder on the intrinsic damping in this in these iron films. And so let's take a look what we measure at room temperature. So these are measurements of two iron films measured in plane, one on magnesium aluminum oxide and the other one on MgO. And like I said, they are structurally very different, but essentially at room temperature, we get exactly the same line widths as a function of frequency. So their damping is virtually the same. Well, now you might say, well, this is measured in plane. Who knows? Maybe you are just limited by two magnon scattering. Well, that is not the case as we can see in this graph. So what we did here is we also did some out of plane measurements where two magnon scattering is absent, and we get again the same kind of damping parameter in the out-of-plane configuration. So we can also conclude that in our films, that the 2 magnon contribution is negligible, which is kind of to be expected because the films were 25 nanometers thick, so any interfacial contribution should drop off fairly rapidly from 2 magnon scattering. So now we really have a system where we think we can measure the intrinsic damping of the material. And so let's take a look at low temperatures. And so this is kind of the data as you get them at low temperatures at 10 Kelvin. And what you see here is the structurally better film on magnesium aluminum oxide has a larger damping. And so this is at first glance might be a little surprising if it weren't for this conductivity-like intraband contribution, which dominates at low temperatures. And so you can obviously then do these measurements at a whole bunch of temperatures. And what you get here is for the film on magnesium aluminum oxide, you can now clearly see that at low temperatures, the damping increases, just like the conductivity increases in this kind of film. If you compare that now 1-to-1 with a film grown on magnesium oxide, you see that this increase, while you might still see it here in this particular film, it is significantly smaller than in the film with a higher structural quality. And again, the reason for this is that we now have a system where we're not limited by interband contributions, but we're rather limited by the intraband damping contribution, which dominates at low temperatures. And what I think is interesting is that you now have a system where you have more structural defects, but you get lower damping at lower temperatures. So that's something that gives you another handle if you're trying to design a material. Defects are not always a bad thing if you're after low damping materials. So that's kind of interesting to see. Which brings me to another topic I want to address in terms of magnetization dynamics. I want to take a look at another slightly more complicated system. This is exchange bias. And if you're not familiar with this, this is the shift of the hysteresis curve in an antiferromagnet bilayer system. And this is caused by frozen spin structure in the antiferromagnet and exchange coupling at the interface to the ferromagnet. So this effect has been used in many spintronic devices to pin the ferromagnet, for example, in hard drive read heads, spin transfer torque, magnetic random access memory, angle sensors, and a lot of other applications. And it's been around for quite a while, but still today there are many open questions for these systems. And people that know me, I actually did my PhD working on exchange bias. And I have to say, when I finished my PhD, I actually said, I'm never going to look at exchange bias again because I've looked at it for in so much detail. But once we started looking at the magnetization dynamics in these systems, it's actually very interesting. So I kind of allowed my students to actually look into this. And the reason for this is the antiferromagnet that you put next to the ferromagnet breaks the symmetry of the system in a way that you have what we call a unidirectional symmetry axis, or symmetry direction, to be precise, where the system behaves different when you apply the field parallel or anti-parallel to that direction. So the question then is, how does that affect damping? And we'll get to this. And so first of all, what you can do is you can do your FMR measurements, again, over a broad frequency range, and you can do it in two basic configurations, where in one case you apply the external field parallel to the bias field, and in the other case you apply it anti-parallel to the bias field. And because of that broken symmetry, these two resonance curves are actually shifted. And from the separation of these two curves, you can actually extract the bias field. And you can also try and extract uniaxial anisotropy that is very commonly observed in these systems. So we can do that, and the curves that you see here actually fits to the data with the parameters listed down there, which is good. But you can actually do a lot better than this, because what you've done here is you just measured along two high symmetry directions of this system. You can actually go ahead and do angle-dependent measurements of the resonance frequency or the resonance field in this system. And that is shown here. So the points here, believe it or not, but these are data points measured with FMR. And this system is iridium manganese and cobalt iron, a system that's commonly used in industry. And it'll become clear why that is in a little bit. What you see here is the experimental data. What we did here is we actually applied two models to the data. And one is the analytical model that you'll find a lot in the literature, because you can write down an analytic expression that makes it easy to fit it. The other one is a little more complicated. You actually take the Smith-Belyas relation, minimize the energy, find the angle of the magnetization, and solve for the resonance field for each orientation. And then you do that in a kind of fitting procedure to actually extract the parameters. So you can kind of see why people might prefer the analytical model. And looking at the data as it presented here, you might say, well, so why bother, right? So why would you use something more complicated when you can get away with a analytical model as it seems? However, what I always tell my students is to look, instead of the data, just looking at the data like I showed before, you should always look at the residual. So how does the fit actually deviate from the data that you measured? And that's shown here. And what you see in the analytical model, you see this kind of systematic angle dependence, which kind of tells you something isn't quite right with that analytical model. Whereas with a full model, you get what you should expect. You basically just get random noise in your residual. So the reason for that is the assumption of the analytical model is that the magnetization is always aligned with the external applied field, which leads to, interestingly, something that looks like a threefold symmetry, which in this case is rather unphysical, I would say. And so the full model then helps us explain where that comes from. Where it comes from is really this assumption that the magnetization is aligned with the field is only fulfilled at 0 and 180 degrees. In between, the magnetization at any finite field will always deviate from the field direction. So that's something that one should keep in mind when using this analytical model. It's pretty good to get a good estimate at first, but then you can do better by using the full model. What do you get out of this? Well, once you do these angle-dependent measurements, you can more precisely determine the bias field here. And then you can do that again for a whole bunch of different samples. And you can, with a little bit of goodwill, you can fit this to a straight line. And from that, you can extract something that's very interesting for applications, which is the interfacial unidirectional energy density. And it turns out that for this system, it's very high, and it's much larger than most other metallic antiferromagnetic materials. And that's part of the reason why this system is so heavily used in applications. What else do we get? Well, so the other thing we get from these measurements is the line widths as a function of frequency. And that's kind of shown here, again, in these two configurations where you apply the field parallel to the bias direction and anti-parallel. And you can clearly see that these two dependencies are clearly different. And if you want, you can try and fit this with a straight line and extract something that I would call the effective damping parameter. And you obviously then see that in the parallel configuration, you get a smaller damping parameter than in the anti-parallel configuration. But if people pay close attention to the data, they might say, well, maybe a straight line fit is not the right thing to do here, because there's clearly some curvature, at least in the red data. And if you look at a thinner film of cobalt iron, you actually see that this curvature gets much more pronounced here, in particular in the anti-parallel configuration, which is a clear indication of two magnon scattering being present in this system. And so that kind of, if I would show you this data with a straight line, you would say, well, that's really not a good fit to the data. Whereas over here, I might just get away with it. The problem with two magnon scattering and the kind of Gilbert damping term that's linear with frequency is you can try and fit a model that includes both. But what you end up with is a whole lot of fitting parameters that allow you to fit almost anything. So this is typically not a good way to try and really extract the underlying intrinsic damping. And so what we see here is at least the effective damping here appears to be anisotropic. So the question is, well, where does that come from? Well, if it's caused by two magnon scattering, that shouldn't be too surprising, because if we look at the dispersion relation of the spin wave in an exchange biased system, we actually get a dispersion relation that looks something like this, where you have the FMR mode and you have all these degenerate spin waves here. And these are the spin waves that the FMR mode can scatter into. And what needs to happen for that is you need roughness at the interface. So you actually have a scattering potential then, so you can actually scatter into those spin waves. So this is the configuration where we apply the field parallel to the bias direction. If you turn it around, you can already see that the manifold that you can scatter into differs from the parallel configuration, and you obviously can do this numerically. And so the bottom line here is, because exchange bias breaks the time reversal symmetry, you would expect that two magnon scattering will reflect this unidirectional anisotropy, or symmetry of the system. But the question is, well, is that all there is? Is it really just two magnon scattering? And in order to at least get a sense of whether this is all that's going on in this system, we need to do a little better in terms of trying to map the symmetry of the system. So what we do here is we actually, at a fixed frequency, we look at the angular dependence of the line widths. And you get this nice cosine dependence of the line widths at a fixed frequency. And you can come up with a model that essentially includes now a unidirectional term that reflects the symmetry of the system. And with that, you can now parameterize this unidirectional contribution to the line widths. And you can do this as a function of the film thickness that you investigate. So this is a whole series of films here. And what you see here is the data points in black. And you cannot, with a simple fit this data set. So it's just a 1 over thickness square dependence. That fit does not work. But you can see that there is such a contribution, but on top of that, you have to add a linear contribution, so 1 over the film thickness, to actually describe this data. So what we think is happening here, while two magnon scattering is definitely a significant contribution to the line widths in those films, there is another term that scales like the inverse film thickness that also contributes to the damping in those films. And this is not the only system we found this kind of behavior in. There have since been other studies where people have found a similar behavior in very different exchange bias systems. So there's more to it than just the two magnon scattering, which brings me back to the Landau-Lifshitz-Gilbert equation of motion that we started off with. And the way I wrote this down earlier was just a scalar damping parameter. But from what we've learned now, we actually know that the reduced symmetry of your system, be it either the crystal symmetry or, like in the case that I showed you, the broken symmetry at the interface, there's actually more to it. And we should rather replace this scalar damping parameter with a damping matrix, where you can actually have different contributions to that anisotropy of the damping, where one just having these different entries would be the so-called rotational anisotropy, and the other one where the entries themselves depend on the magnetization. These are called orientational anisotropy of the damping. And so with that, what you get then are is a damping that can be very different along different orientations of your crystal or your system, if you look at a bilayer system like we did here. So that brings me to a brief summary. So I hope I kind of showed you a little bit how the LLG equation of motion is a very suitable tool to describe the equation of motion or the magnetization dynamics. I showed you how you can use broadband FMR to probe the magnetization dynamics and learn a whole lot more about the damping than by just measuring at a single frequency. In iron, we were able to show that the intrinsic damping appears to be dominated by spin-orbit coupling, which leads to this conductivity-like term that dominates at low temperatures, where better structural quality of your film doesn't necessarily mean a lower damping. I hope I also showed you that damping can indeed be anisotropic, but in this regard, I think we've only scratched the surface. But one also needs to be very careful not to mistake anisotropic damping with contributions that come from two-magnon scattering. With that, I would like to thank all the people that contributed to this work, in particular Satoru Emori, Christian Kaiser, with whom we worked on different projects, and obviously all the students that did the actual work, the current graduate students. Most of them are shown here in the picture. We're having a hard time getting everybody together these days for an updated group picture. We have some former students that some of you might be familiar with that are listed below. And with that, I'll open it up for questions. Thank you.
Thank you very much, Professor Mewes, for the very nice talk. And we can give a round of virtual applause by clicking the reactions buttons at the bottom of the screen. So this talk is open for questions. Please use the raise hand button located in the participants panel on the bottom of the participants panel. So the first question will be asked by Professor Minzhong. Please go ahead and unmute and ask a question. Minzhong, you have to unmute yourself.
Hi, team. Very good talk. One quick question. So for the FMR on the exchange biased system, did you try to run FMR with a perpendicular field?
Yeah, I know somebody would ask that question. The problem there is that once you let me go back here. So once you go in the out of plane direction, the bias was actually set in the film plane. So the bias was set in the film plane. If you go out of plane, it doesn't matter whether you go up or down. It's the same from the symmetry point of view. It's the same configuration. So you would get the same result whether you measure with a field up or down. So the obvious choice here would be to use a system where you can get the system bias perpendicular and then measure with a field up and down with respect to the film normal. And that's something, it's not that we haven't tried. The problem there is, in order to get it perpendicular, you typically need some adjacent layers that tend to really broaden the lines of those thin films. So it's a tricky experiment.
Yeah, thank you. I think it's interesting to have a perpendicular exchange bias. They look at the possible argument about the two-magnon scattering.
Exactly. That would immediately eliminate the argument about the two-magnon scattering. And if somebody in the audience has a good perpendicular system, we're more than happy to give it a try. So far, we haven't gotten any samples that we were actually able to really get a decent ferromagnetic resonance. They're typically too broadened. There are a couple of reasons for that. But.
Thank you.
Second question will be asked by Professor Hillebrands. Please unmute and go ahead with the question.
Yeah, thank you very much, Tim, for your very, very nice work. And I also found it extremely nice that you are still looking into this anisotropic damping and exchange bias system. My question is just the following. I mean, originally we had some kind of hypothesis that we were saying if the fluctuating exchange bias fields are perpendicular to the direction of magnetization, we have a much stronger damping than if they would be along the direction of magnetization. You remember, because the damping is more sensitive to fluctuations in the direction of the magnetization than to the length of the magnetization vector. So does this old, very simple hypothesis still hold?
I think if I understand your argument correctly, I think what that would refer to would be the two-magnon contribution. So, because it's your scattering potential here that, but in terms of the, if you think in terms of the electronic structure, so what we are thinking might be happening for this additional contribution that is not or doesn't seem to be linked to two-magnon scattering. The hypothesis here is that at the interface you actually modify the electronic structure of the system, and again you have this broken symmetry where essentially now your electronic structure reflects that unidirectional symmetry of your system, and therefore such a term should be allowed. It's just not clear whether it can be as big as what we've observed. So that's something, but yeah, one has to be careful not to kind of, well, just seeing a difference in the line widths between parallel and anti-parallel. In most cases, this will be caused by two-magnon scattering, which is very sensitive to these fluctuations because the scattering potential enters squared. Does that answer your question?
Yes, okay.
Okay, the third question will be asked by Dr. Tom Silva. Tom, please unmute. Yeah.
Yeah. Hey, Tim. Thanks for the talk. That was really enjoyable. I really like the work you put into getting the nice slides together too. Those were fun. So this is just an experimental detail question. You kind of dismissed the difficulty of getting out to 115 gigahertz as just a matter of making a good microwave circuit. Would you mind elaborating on the challenges that an experimentalist actually has to overcome in order to be able to
that
high frequency?
I can elaborate on the challenges, but I'm probably not going to elaborate too much on the solutions to that. So it is actually very difficult. So a lot of it is just the design of your microwave circuitry. So a lot of people struggle with that, and we've struggled with that too initially, just to get coplanar waveguides, let's say working up to 40 gigahertz, let alone to 65 or more gigahertz. So that's a real challenge. And in the end, what paid off is well, you do some finite element simulations to try and get a sense what the actual dimensions should be of your circuitry, and that isn't too hard. But then the problem is the parameters that you get from your manufacturers, they don't really match what they claim they should be, especially at those high frequencies. So what we did is actually we did a variation. So let's say we had a certain gap width, and I know that Tom knows what I'm talking about. So you have a certain gap width that your simulation tells you should get you the optimal transmission. But then you do a variation and then pick the ones that actually works the best in real life. So you just don't rely on the simulations too much. But yeah, it is very challenging, even just getting a source that goes up to those frequencies. And gives
Can you tell us who made the waveguides for you?
That's actually a company. You can take any, I mean, if they make microwave circuits, they typically know what they're doing. And what you do is you send them your drawings and they do the best they can. And yes, we had a couple that didn't do too well, but you just have them send you a sample and then you would see. But I can tell you more details offline.
Okay. Thanks, Tim.
You're welcome.
Okay, so the next question will be asked by David Edwards. Please go ahead with your question.
Yes, I wonder if you did any studies of thickness dependence of the damping in iron. There's some very interesting paper of Stuart Parkin with a Chinese group a few years ago on permalloy, which showed that they could separate clearly a bulk and a surface contribution to damping. And they found that the bulk damping just had a monotonic temperature dependence without any conductivity like contribution, whereas the surface showed interesting temperature dependence with a big increase up to a maximum as you lowered the temperature. This suggested then that the so-called conductivity contribution, it was associated with surface rather than bulk. I wonder if any comments on that.
Yes, so with the iron, we actually did a study of several thicknesses. I didn't mention that in the talk, not to confuse. So we actually, the films that I talked about were 25 nanometer thick. The reason for that is to actually minimize interfacial effects. We also had thinner films, and I believe we had even thicker films. We did, as I recall, we did not see any significant kind of difference, or we did not identify any temperature dependence of an interfacial contribution. So that was not something we did see. But what you have to keep in mind, these films that Satoru grew in his groups, these are extremely high quality. I mean, I've grown things on MGO before, so the iron films on MGO are typically pretty good quality to begin with, but on this other substrate, the crystal quality is really excellent, and that is really the kind of important difference, because if, as you recall, and I maybe could go back, but as you may recall, the temperature dependence for the films with that were less of the lower quality here on MGO, you don't see much of a temperature dependence. Although once you've seen the data here on the left-hand side, you might actually believe this fit with the orange curve here. But again, this would be what you kind of refer to as the bulk, because we are talking about 25 nanometers. So it would be very difficult to say anything about interfacial contributions here. And that would be, I would have to look at the paper. It can be very difficult to actually disentangle interfacial contributions really to the damping from the two magnon scattering contribution. So that's another complication you struggle with. Does that somewhat answer your question?
Yes, yes. I mean, it seemed quite a clear separation with Parkin's work, and they said there must be two different mechanisms for bulk and the surface, which was interesting. Because as you probably know, I don't believe in intra-band transitions, so I'm always looking for a different explanation of these conductivity-like results.
So in our paper, if that interests you, there is actually in the supplement there is data from other film thicknesses, and this kind of behavior that you see here, that's actually independent of, or well, you see it in thinner and thicker films, so it's not an artifact of this particular thickness.
Okay, thank you.
More questions?
So we're gonna move to Twitch questions. I'm gonna read the questions from Twitch to you, Tim. The first question is, can you give more insight into the dependence of the two magnon scattering on the film thickness dependence?
Yeah, well, this is actually, that has been discussed quite a bit. I'll go back here. So there's work by Resende where this was discussed in quite some detail. So what we're talking about is this dashed line, which is essentially just the 2 magnon contribution that you can actually fit this data for the 4 nanometer film with just the 2 magnon contribution. The problem with 2 magnon contribution is in order to come up with an analytic function that you can fit to your line width data, you have to make an assumption about the roughness of your films. So you actually have to come up with a model for the roughness of your films. And depending on what assumptions you make, the analytical function that you get is going to be different. And there's been some, I think Resende was one that discussed that in the past. And if the person is interested, they can shoot me an email and I'll find the references. There's work by Mills as well, where they discuss that in a little more detail. But that makes it even harder to actually uniquely identify this kind of dependence. What 2 magnon scattering typically has in common is that at low frequencies, you can describe it approximately linear, whereas at high frequencies, at some point, it should saturate. So that's kind of the common things that you expect from 2 magnon scattering. The details then really depend on what model you use for the roughness at the interface.
Thank you. And the second question is, how is damping impact on the spin orbit torque switching? Is asking about the spin orbit torque devices.
Yeah, so for spin orbit torque switching, the current density that you need to switch, if you lower the damping, you can switch with lower with lower current densities. So I always when I talk to my students, I always tell them, well, when you measure the damping in a material, it doesn't matter whether the damping comes out to be low or high. It's going to be useful for something, because people in the hard drive industry, they actually would rather have a material that kind of damps out these oscillations, and therefore a material with a high damping can actually be, at least in some cases, be useful. But yeah, for spin torque switching, you definitely want a material with a very low damping.
Thank you. And the third question is, what is the difference between damping constant of amorphous and crystalline material?
What's the difference? Well, for an amorphous system, you would not expect any anisotropy whatsoever. However, for crystalline materials, this anisotropy tends to be very small to begin with. Other than that, I'm not sure what the person asking that question is.
I think he's asking if there's a specific contribution from the amorphous material or crystalline material to the damping constant.
Yeah, that's a tricky question. I would have to think about that a little longer to
Sure. I'll just if that the question still have that question, please directly email Professor Mewes.
I would be interested to learn what the person is looking for.
Sure. Okay, I think that's all the questions on Twitch. Do you have any other question in Zoom? Dr. Silva, please go ahead with that question.
Yeah, Tim. Another question came up with regard to your measurements on iron, the single crystal iron measurements. It looked like you had a different, you had the same damping for in plane and out of plane. I think it was that slide. You had the same damping for in plane and out of plane, but you had a different inhomogeneous broadening. Yeah, that one.
Yep.
So any idea why there would be an anisotropy for the inhomogeneities in the system?
Yeah, that's, well, you can see that in, typically we see that in films that have perpendicular anisotropy. So there things can be different. And for those films, if you have a system with a perpendicular anisotropy, you actually expect the inhomogeneous broadening to be larger in the out-of-plane configuration than in the in-plane. However, in this case, I'm actually not quite sure what's causing that. So we haven't looked into that into more detail, if that's your question.
And these were thicker films, right?
Right. These were thicker films. And so yeah, that what I'm saying is it's not uncommon, but the reasons for that, we haven't looked into the details why that might be the case.
And then I was just wondering, in this data set, you've done extremely high frequencies for the out-of-plane measurements as compared to the in-plane. Is there some reason why you have to be at such high frequency for the out-of-plane?
There are. So one reason is you definitely want to saturate your film out of plane, and we're talking iron. So you need to be at least at a little more than 2 Tesla. So that's part of the reason. Others are then, yeah, well, you kind of, at some point you have instrumental limitations that, which actually limit us to go to lower frequencies. Yes, we would have loved to go to lower frequencies, but in this particular case, we couldn't do that.
Okay, thanks.
Satoru, please go ahead with a question.
Uh-oh.
Oh, no, it's not a question. So it's kind of a follow-up, I guess, to what Tom was asking about the difference in delta H naught, so zero frequency line with out of plane versus in plane. So I don't know that I have a concrete answer, but somewhere I think it was a book chapter written by Brett Heinrich or somebody that mentioned that this kind of difference could arise because of the difference in the shape of the precessional orbit. So somehow, you know, with the precessional orbit not being elliptical, more circular for the out plane, you may end up having, I guess, higher sensitivity. You know, the zero frequency line width might be more sensitive to some kind of homogeneity. But I don't really quite understand how this really works, but this is something that I have seen.
Yeah, that's actually correct, and that's what I hinted to with if you have a system with a perpendicular anisotropy, that's the same kind of argument there. It's essentially when you have these elliptical orbits for in-plane measurements, you're actually not as sensitive to variations of the perpendicular anisotropy as when you're measuring in the out-of-plane configurations. Whether that's the case here, I doubt it because we haven't seen any noticeable out of plane anisotropy on those films. But it is something we've seen in other material systems, that your out of plane delta H naught can be larger than in plane, or is quite frequently is larger than in plane.
Okay. If there's no other question, I want to thank the speaker again, and I want to thank all of you for participating.